All right, so now we are looking at the next aerodynamic force that we have. So the first aerodynamic force we looked at is lift, because we want the aircraft to be airborne. So we need something to counteract the weight, which is lift. Now the next aerodynamic force is, it's not that you just have to have the aircraft just airborne. We want it to move forward, and if the aircraft wants to move forward, it has to overcome drag, right? We use thrust to overcome drag. So next aerodynamic force which we are concerned about is drag. So we'll talk about drag now. Now, if you have understood lift, pretty much drag is very, very easy. And we have also seen how relatable the drag and lift are. And we have also seen that wherever there is lift produced, you have one or the other form of drag coming into picture. And we have also seen the lift equation. We have written side by side the lift and the drag equation. And we have seen how comparable those equations are, right? So what is the drag equation? Drag is again an aerodynamic force, which is D. It's the product of coefficient of drag. Then what remains is exactly common for lift and drag equation, right? So this is the dynamic pressure Q, and then we have the aircraft wing area, right? That is, drag is equal to coefficient of drift into dynamic pressure into wing area. So what do you understand from this? So if I write the lift equation and drag equation side by side, so lift equation is coefficient of lift into dynamic pressure into wing area. What do you understand from these two equations? So look at these terms here. The product of dynamic pressure and the wing area contributes to both lift as well as to drag, right? So when I say that I have a very large wing, it can produce so much of a lift. I'm flying so fast, it has so much of dynamic pressure, so much of lift is produced. I should also understand that it's also going to produce drag, not equal, because drag is not going to equalize lift. Weight is the one that is equalizing lift. Drag is going to equalize with the thrust, but not equal, but definitely in proportion. It's going to change, right? That is why we have also seen the lift drag ratio, and we have come up to a optimum angle of attack, which is alpha is equal to, what is the optimum angle of attack? Too many answers won't make it right. One answer. 4 degrees. Yes. Don't come with 16 degrees. 16 degrees is the stalling angle of attack. That's right. So you can see how that lift drag ratio. Remember the curve for lift drag ratio? It's somewhat like this. And yeah. So this alpha is equal to 4 degrees, which is what is called as the optimum angle of attack. So if you fly at the optimum angle of attack, it's not that you're going to have the highest lift. It's not that you're going to have the lowest drag. For the highest amount of lift, the least amount of drag possible is available at alpha is equal to 4 degrees. And we have also seen why lift drag ratio is reducing for angle of attack less than 4. That's because the lift produces very, very less. But for angle of attacks greater than 4, the lift is actually higher, but the drag is also going to be higher. Remember the lift, take for a symmetrical wing, the lift coefficient, stall and comes down. This is lift coefficient. And for drag coefficient, it doesn't stop, it keeps going up, right? So if I hope all these things are there in your brain, but I'm just doing a recap because it's quite long since you have seen all these things. But what I'm trying to tell you is that, so it's not about having the highest amount of lift. It's not about having the least amount of drag. It's about having the highest amount of lift for the least amount of drag possible. And that is what we represent by using lift bar drag ratio. Lift bar drag ratio depends on angle of attack for a particular configuration. Doesn't matter whether the aircraft is heavy or lighter, the aircraft is still going to have the best or a maximum lift drag ratio at alpha is equal to 4 degrees for a given configuration. We have done all these questions, so go back to all those things. Make sure you read all these things up. It's not like every subject I take, I just say the same thing, but it's not like your other 3 subjects. It's very, very easy to forget this completely. It's not like you have bits and pieces here and you know things. No, after a week, if you don't look at it, you will have zero knowledge about it. It's the same thing with me, not just with you. If I don't look at this for a year, I'll really have to turn back and start reading once again, because the retention of all this knowledge is not very great, and you keep forgetting it, right? What is a very nice topic. All right, perfect. Now drag. Let's come back to drag equation. As I said, a good understanding of lift equation will actually help you with your drag as well, right? Now, what is the reason for drag? So why do you think, so when you put your hand outside a fast moving car, you can physically experience drag. And probably even more than lift, what you're going to experience is drag. You can see your hand getting pushed behind. It's not that just getting pushed behind like this, it's also probably going up depending upon the angle of attack you give, but most probably what you will feel is the drag that is pushing you rather than the drift that is pushing you up. Now, so what do you think is the reason for the drag? Why do you experience drag? That's because you have introduced your hand into an airflow that is perfectly undisturbed before. And all of a sudden you open the window and you put your hand outside, you are introducing your hand into the airflow that is going to disturb the airflow. Perfect. Now, what happens when you have an aerofoil introduced into an airflow, a relative airflow you can talk about. We have seen this thing before as well, but I need to explain that once again because we're talking about drag specifically here. Now, think about an aerofoil like this. Let's start with a symmetrical wing, right? Now, will this wing produce lift? A symmetrical wing, will that produce lift at this particular configuration? Now think about it, this is a code. Straight line joining centers of curvature of the forward leading edge and the trailing edge. And you have the relative airflow that is coming from here. Is this wing going to produce lift? It will not produce lift. First of all, the angle of attack is going to be 0. Therefore, the wing is not going to produce lift, effective lift. Now, so you have a boundary layer here. You also have a boundary layer here. The reduction in pressure is kind of equal on both sides. That the effective lift is going to be 0. Now, what can I do to induce lift on this particular symmetrical wing? I need to change the angle of attack. That is the only thing which I can change, right? Otherwise, the CL is going to remain 0, right? Perfect. So in this particular configuration, you've seen all these things before. That's why I'm just rushing through it. The lift is going to be 0. What about a wing of this stature like this, which is kind of camber?
It will produce lift because
it will.
The pressure is,
So even though the angle of attack is 0, so if I make the chord line here and I make the relative airflow come straight in line with the chord line, angle of attack is 0. But it is still going to produce lift because the cambering is not symmetrical. Correct? So the static pressure is going to reduce more here. It's going to reduce here also, but the reduction is more here. Effective lift is going to be produced in that direction. Therefore, this is going to produce lift. That is what, even at 0 angles of attack, you will have lift production, and that is because of cambering. And that is what contributes to coefficient of lift, which has both alpha as well as camber. Or think about coefficient of lift as the capacity of an airfoil to generate lift, right? Now, if I want to generate more lift here, the cambering is going to still remain the same. Now what I'm going to do is I'm going to increase my angle of attack. Now the airfoil can derive more lift, and therefore CL actually starts increasing. So when I increase the angle of attack, so angle of attack is the angle between relative airflow and your chord line, right? So the angle of attack has increased from 0 here. What happens to lift? The lift produces L here. The lift is actually going to increase, right? You're not really bothered about lift here at the moment. You're talking about drag here. Now, when you increase the angle of attack, what have you done? In a more physically or more practical way, if you think about it, we can come back to the equation here, but still think about it. Earlier, so as I told you, why did you experience drag? Because you put your hand outside the car, you introduced your hands into the airflow. And now the air is going to come and hit your hand and kind of slow down. And by Newton's third law of motion, it is going to give you a reaction which is experienced as a drag. The entire car is also having the same drag. That is why if you look at the speed cars and stuff, it's more streamlined. It's more curved and streamlined. So if you look at this particular wing here, both these wings, only so much of an area of cross section. If I can draw a tube here, just to make you understand, only so much of a cross section is actually introduced into the aerofoil. Correct? What happens here? See the cross-sectional area of the aerofoil that is introduced into the airflow. It has increased, and that is going to increase the drag because now the air is kind of hitting all these surfaces. You have introduced all these surfaces into the airflow, and that is going to create drag because the air wants to continue its motion. Now you have something hindering that, and that's going to create a reaction, which is what is called as drag. That is also going to produce lift, right? Because it is hitting in an inclined manner. It's gonna produce a net force in that direction also, which is what we call as a lift. So it is going to produce lift as well as it's also going to produce drag, right? So both your lift as well as drag increases. The drag is going to be smaller here. The drag is going to be bigger. It's not equal, so don't think that it is going to be same, but it's definitely going to increase. Now initially you will have a higher increase in lift than drag, right? That is why when you take off at smaller stages of flaps, because you get more lift there. You do get drag, but the drag is comparatively lesser, right? But when you come for landing, you need more drag. And why do you need more drag? That's because you want to stop the aircraft as quickly as possible. So you switch into higher stages of flaps. So higher stages of flaps are going to produce more lift, but it's also going to produce more drag. And the drag introduced by flaps at a higher stage is much more than at a lower stage. Now think about it. If I increase the angle of attack further of a cambered wing, now what have I done to the angle of attack? I've pitched up more, angle of attack has increased. What happens to lift? Lift is going to increase. But what happens to drag? Drag is also going to increase, but you will reach a point where the increase in drag is going to be much higher than that of the lift. So it's not that when you increase your angle of attack, there reaches a point where lift stops increasing. No, lift will continue to increase, but drag also will continue to increase. And after a particular stage of angle of attack or flaps, take for example, if you put the flaps, then the increase in drag is going to be much higher. Now, can you keep increasing the lift like this by pitching up and increasing the angle of attack? So we know the lift, it will stall. You see, we have, the equation, the graph connecting coefficient of lift and alpha. For a symmetrical wing, what happens as you increase the alpha from 0, it keeps the coefficient of lift increases. That's because alpha is increasing. It reaches a point where the pressure gradient reverses and the aircraft starts losing lift, and that is what is called as a stall, right? That is what is called as a stall. Now think about the variation of coefficient of drag. Do you remember how coefficient of drag is varying? Even at 0 angles of attack, you have some amount of drag. The angle of attack is 0, you still have some amount of drag because you have an aerofoil in the air that is going to create resistance. So even at 0 angles of attack, you have some amount of drag. Now what happens as you increase the angle of attack? The drag is going to increase. What happens to drag after stalling angle of attack? Is the drag going to decrease just like lift?
No, sir.
No, it continues to increase, correct? Drag keeps on increasing. You can see that here. Drag keeps on increasing, but lift will reach a point until alpha stall, after which the lift is going to reduce, but the drag will still keep increasing even after that. So did you understand the reason for, one of the reasons for drag is your aircraft itself. The aircraft, the whole idea about the aircraft being in that air is causing drag. So every single part of the aircraft is responsible for drag. And that is why you think about it, look at an aircraft that is taking off, bigger jets. And one of the first things that you would see is the retraction of the landing gear. Why do you think that is required? So when you will learn eventually, when you start your flying, you will hear this, that the moment you see a positive rate, the first thing you do is you gear up. Remember, we studied the different stages of a takeoff climb. And one of the things that you do from 35 feet is you look for a positive rate and you gear up. The first stage of the takeoff climb, right? Why do you think that is done? Landing gears are not very aerodynamic. They have tried to make it as aerodynamic as possible, but they're not aerodynamic. There's wheels and all your struts and stuff. Therefore, they are not very aerodynamic. The quicker you get that inside, the quicker you remove the drag. Understood? Same thing with the flaps also. When you remove the flaps, you lose lift, but you also lose the drag. Does it make sense? The whole idea about your aircraft being in the air itself causes a drag. So you can divide drag into basically two different categories. All right. So let's see that. It's there in your note, the classification of drag. There are two different types of drags. Now think about the aircraft as a whole, the aircraft surface, the surface of your car. Everything is responsible for drag. Now why do you think your umbrella catches wind? That's because the whole surface of the umbrella is a drag causing surface. And have you experienced lift from the umbrella? If you point umbrella in the right angle, the umbrella is going to create a lift also at the same time. Right? So the whole umbrella itself, or the whole aircraft or the car itself, is the cause of drag. So any surface that is causing drag, that is what is called as a parasitic drag. Or it's called as a parasitic surface, and the drag is called as a parasitic drag. Right? So what happens if I introduce an aerofoil of this kind of a structure? What do you think the drag would be in comparison to an aerofoil like this? Which of this is going to produce lesser or more drag? Say for example, more drag. The first one or second one?
First one.
The first one, right? That is because this is not favoring a streamlined airflow. This is also not completely favoring a streamlined airflow, but relatively or comparatively, this will make it more streamlined. You see how the fishes are all designed, or the birds are all designed. It's not that those surfaces are not producing drag, they're also producing drag, but the drag is kept as minimum as possible. All right, so, but even then this surface is going to produce drag. Think about it. What if I have some kind of ice here? This is a critical thing with ice formation. This has kind of distorted the streamlined shape of the aerofoil, right? And therefore, what happens to drag? The drag is going to increase. Yeah, dirt, ice, all these things can increase the drag, right? So that kind of a drag, which is caused because of the ultimate structure or form, F-O-R-M, form of the aerofoil, is what is called as a form drag. So look at the word form here. Form means the structure, the form. The drag because of that is what is called as form drag. Now, how do you think I can reduce a form drag given these two structures? I would probably choose this one, not with the ice. Yeah, this one. So this will reduce my form drag. So why do you think it reduces the form drag? Because this structure is more streamlined. That's the term. So you see why fishes are in the way they are, why birds are in the way they are. It's all streamlining. That is why you see all race cars and stuff. You can see they are more like not this stature like the normal cars. They are more like relatively curved, which is kind of giving them a very streamlined structure. The air should not feel that it is kind of hitting something, but it will. But the least it can feel, the better, right? That's the whole idea. So, what is one of the best ways to reduce form drag is by streamlining. Does it make sense? Understood? That is one of the forms of the drag because of the ultimate structure of the aerofoil, right? Now, there's another type of drag because of the air. So think about it. Now, what happens to the air when it actually blows over the aerofoil? What happens to its velocity in general? So as I told you, the velocity of the airfoil, air is V over here. Forget about aerofoil. Any given structure introduced into the airflow, what happens to the velocity? The velocity is going to reduce. And what is the reason for reduction in velocity? That happens to everything. Take a ball and just roll the ball. Newton's first law states that the ball should continue its motion. But it also states that unless compelled by an external force. And what is that external force? You can see the ball doesn't keep rolling infinitely or indefinitely. It will stop at a point. That's friction. Yes, the friction is the one that is stopping the ball. If nothing else matters, friction will stop it. Wind. Why do you think the wind as it comes down kind of backs? because the ground friction acting on the wind will reduce its velocity and the wind backs, right? It's all friction. Same thing happens here. However streamlined you make it, there is some amount of friction that is introduced which causes a drag, which is what is called as the friction drag. Skin friction. So first thing, form drag is because of the ultimate structure itself, and second is because of the friction with the skin. That is what is called as a skin friction drag. Right? Now skin friction drag is not very significant with lower aircraft like your training aircraft, general aviation aircraft and stuff. Not general aviation, but training aircrafts. They're slow moving, therefore the friction is also less. But think about aircrafts having a velocity, especially TAS of like 300 knots or more. We have the compressibility factor coming into picture. The skin friction drag is going to be more, right? So we'll see that a bit later. But did you understand these two drags? The first one is form drag and the second one is skin friction drag. Skin friction drag also can be reduced by making sure that your surface is as clean as possible, right? Now tell me, what is one of the techniques that we use to reduce friction? Generally, day-to-day life, you want to reduce friction. What do? Oil, lubrication, right? You smoothen the surfaces, grinding, all those things can help you reduce friction. Which means, what are you trying to do to the surface? You're trying to polish the surface, make it as smooth and clean as possible, right? So that's right. So make sure before you fly, the wings are clear of dirt, clear of ice. It's all gonna improve so reduce the skin friction drag. Right? And reduction drag is going to actually help us a lot. It's going to reduce the thrust required, and no, it all comes down to fuel and stuff, right? This might seem to be very, very silly, but remember, we're not flying at say 10 knots, 20 knots, 30 knots. We're flying at say 600 knots or 500 knots. So very, very small factors can actually amplify all the way up there. Make sense? Now there is a third type of drag, which is again parasitic drag. The parasitic drag is because of parasitic surfaces. So first one is a form drag, second is a skin friction drag, and the third one is what is called as interference drag. Right? Not very well explained in the textbooks, but basically, let's look at some surfaces here. Now, if you look at an aircraft, look at next time when you fly, probably try looking at the tail section of the aircraft. You see what I've drawn here is more like a very abrupt, sharp corner, a point. Right? What do you think is going to happen to the air as it reaches here? Have you seen, if you go to water slide or something, there's a tube, there are bigger all these water theme parks. They'll put you in a kind of a raft or something, and they'll just push you all the way through, and they put water through it. Have you seen that? The water flows through it, and you're actually flowing with it through tunnels. And how do you think those tunnels turn and twist? Is that it's going to turn and twist very abruptly? No, that won't work. They kind of make it curved. Make sense? Now, why do you think that is? And think about you going and hitting a corner like this. It's gonna reduce your velocity instantly. The same thing is going to happen to the air here. You'll crash now, you can come back. It's going to happen to the air here. Next time when you fly in bigger aircrafts or even for smaller aircraft, look at this section. This is going to be more curved. It's what is called a fillet. And you very well now know why is it curved. Because the air is going to just slide all the way smooth. It is still going to produce drag, but lesser. That's all. Make sense? So the drag that is produced by corners, edges, etc., is what is called as the interference drag. They interfere with the airflow, and it's called interference drag. Right? We'll close and come back. I'll keep the diagram on the board.